Good day, colleagues, session chairs, and fellow researchers. Welcome to my presentation. My name is Douglas Dube, a PhD student from Botswana International University of Science and Technology. Today, I'm honored to present our comprehensive review entitled Synergistic Efficiency Breakthroughs in Dye-Sensitized Solar Cells Through Co-Sensitization Strategies and Performance Trends, looking at studies from 2020 to 2025. This work was compiled alongside my supervisors, Dr. D. Murape and Professor C. Nyamere. The primary motivation of our comprehensive review is the global transition towards sustainable, scalable, third-generation photovoltaics. Dye-sensitized solar cells offer immense potential due to their low-cost fabrication, mechanical flexibility, and excellent performance under diffuse light. However, traditional single-dye systems, they have physical limitations. And over the past 5 years, the global community has seen a paradigm shift away from the traditional single-molecule sensitizers toward multi-component molecular engineering. In this presentation, I will dwell on how co-sensitization serves as the structural foundation for achieving high power conversion efficiencies, while also evaluating the critical conflicts that can impede device stability. When we look closely at a single dye sensitizer, it possesses a narrow solar spectrum absorption range. Furthermore, at high loading concentrations on the titanium dioxide photoanode surface, these molecules are prone to molecular aggregation, which induces exciton quenching. Instead of transferring the generated electrons to the semiconductor, the excited energy is lost non-radiatively between neighboring dye molecules, and this decreases the electron injection efficiency. When we look at the plots that we have, we can see that dye 1 absorbs heavily in the lower wavelengths, whilst dye 2 absorbs further up the visible spectrum. And by utilizing the co-sensitization technique, we combine these complementary dyes onto a single photoanode surface, and the resulting red curve represents the co-sensitized system. It broadens the overall spectral response, it optimizes the underlying charge transfer dynamics, and also increases the chemical anchoring density on the mesoporous oxide. There are two key techniques that are employed when it comes to deposition, namely the cocktail approach and the stepwise or the sequential approach. In the cocktail approach, the titanium dioxide substrate is immersed into a single solution that contains a pre-calculated mix of the several dyes that are being used. Whilst this approach offers rapid processing and reduces industrial manufacturing time, it induces severe chemical competition between the dye molecules or the active binding sites of the semiconductor. Normally, dyes with stronger anchoring groups or smaller kinetic diameters will dominate the surface, and this leads to uneven distribution and uncoordinated phase separation. On the other hand, the stepwise method, it utilizes consecutive emission cycles. As shown, we can see a bare titanium dioxide photoanode that is first dipped in dye 1. This creates a controlled primary monolayer. Then after rinsing off unanchored molecules, the substrate is immersed in dye number 2. This ensures that dye 2 molecules systematically fuse the remaining interstitial voids. The outcome is a dense, highly controlled, and uniform layer-by-layer packing arrangement. Literature proves that this sequential technique results in higher device efficiencies due to improved surface coverage and reduced charge recombination. There are 3 pillars of current density enhancement. The first pillar is panchromatic harvesting, whereby traditional visible light absorbing dyes, they are paired with advanced near-infrared sensitizers, extending the photon absorption threshold up to wavelengths around 950 nanometers. This broad capture increases photocurrent generation. The second pillar is Foster resonance NH transfer. In several systems, secondary dyes possess excellent absorption properties, but they have poor chemical anchoring groups, which prevents them from transferring electrons directly to the titanium dioxide. Through FRET, these non-anchored molecules act as antenna units absorbing the light and transferring that energy non-radiatively via dipole-dipole interactions to an anchored acceptor dye. And this improves the current density. Then the third pillar is aggregation mitigation, which is achieved via interstitial packing by geometrically designing secondary filler dyes that are smaller or structurally tailored. We can physically displace inactive insulating additives. These filler dyes, they position themselves in the microvoids, blocking molecular aggregation whilst actively contributing to photon collection. Whilst the current density deals with light harvesting, the open circuit voltage depends entirely on thermodynamic energy levels and interfacial charge transfer kinetics. Let us review the interfacial engineering principles using the energy level diagrams. On the left, we have the titanium dioxide interface before modification, and we can see a major loss pathway labeled K-back, which represents the destructive recombination of injected electrons in the semiconductor's conduction band back to the triiodide species within the liquid electrolyte. And on the right-hand side diagram, we have passivated titanium dioxide interface after core sensitization and surface engineering. The dense packing of core sensitizers creates a physical insulating passivation barrier. This suppresses the K-back rate. Additionally, the chemical absorption of specific surface dipoles causes a negative energetic shift in the conduction band edge of the titanium dioxide. Because open circuit voltage is defined by the potential difference between the Fermi level of the semiconductor and the redox potential of the electrolyte, this upward shift directly increases the voltage. Electrochemical impedance spectroscopy tracks this exact progress, showing reproducible voltages, gains increasing from baselines of around 0.7 volts to 0.9 volts. A fascinating trend has been observed during our 2020 to 2025 literature analysis, which is the divergence between relative signage and absolute efficiency. The data clearly demonstrates that core-sensitized systems that exhibit the highest relative signage gains, most of the times they exhibit the lowest absolute power conversion efficiencies, oftenly in the range or with values less than 2%. Analyzing the data that we have in this table, extracted from a key study of 2022, we can see when evaluated the single dyes Rosil and beta leaves, they produce extremely low individual power conversion efficiencies of 0.31 and 0.40% respectively. However, when they are combined into a core sensitized system, the resulting cell has a current density of 29.47 milliamps per centimeter squared and 1.85 millivolts, a fuel factor of 58%, and also the power conversion efficiency of 1.63%. Mathematically, this represents a signage jump of 307.5%. Why does this happen? Normally in natural extract systems, individual dyes, they suffer from severe raw impurities and poor stand-alone spectrum matching. When they are now combined, their raw components complement each other's spectral gaps very well, producing a gain in the signage, although the absolute electrical output remains low due to poor charge injection. Over the last few years, synthetic, organic, metal-free core sensitizing systems, they have systematically given efficiencies above 10%. In fact, the world record efficiency that is cited in the contemporary literature stands at 15.2%, which was SL9 combined with SL10 dyes. This represents a profound structural milestone for metal-free dye-sensitized solar cell technology. These synthetic dyes, they produce high efficiencies because they have exceptionally high molar extinction coefficients, and they are also highly tailored. They also have highly tailored anchoring groups. And looking at the table that we have, we can see a combination of LG26 and Y1 system, a key study from 2022. Individually, they exhibit highly asymmetric power conversion efficiencies of 9.01 and 2.05%. When core sensitized, they reach an absolute efficiency of 10.45%, which represents a 16% positive signage jump. Similarly, we also have a 2024 acid base pairing that we are seeing here, MD1 and N3, that yields an absolute efficiency of 10.35%, representing an 89.9% signage gain. And finally, looking at DZ102 and TZ101 configuration, we have conversion efficiency of 10.9%. These high performance metrics, they prove that precise synthetic tuning eliminates surface recombination while maximizing panchromatic photon collection. However, it is worth noting that co-sensitization is not a universal guarantee of performance enhancement. There is a risk of negative synergy. When critical dye mismatches occur, the resulting molecular interactions induce highly antagonistic effects, and in these cases, the combined electrical output of the co-sensitized cell, it drops significantly to values that are less than those of the primary single dye alone. This destructive phenomenon normally occurs through competitive displacement. If a secondary lower performing dye possesses a higher kinetic binding affinity or speed, it will displace the high injection primary dye from the titanium dioxide surface. Let's look at the data that we have in this table. The standalone ruthenium dye N719 has a baseline efficiency of 5.3% with a short circuit current of 13.9 milliamps per square centimeter. When mixed with the organic dye Porter, the Porter molecules, they alter the self-assembled layer, then the current drops to, or the current is at 15.04 milliamps per centimeter squared. The Q factor at 37%, but the resulting co-sensitized cell, it is giving a power conversion efficiency of 4%, which is less than the 5.3 baseline efficiency of N719. This represents a synergy loss of 24.5%. This clearly indicates that uncoordinated dye pairing can destroy high-performing single dye baselines. As we draw our look to the future, our review identified a massive current gap in the global literature, which is the reliance on highly inefficient trial and error pairing methods. This slows down discovery and leads to negative synergy outcomes. To overcome this, our proposed solutions are as follows. First, predictive computational modeling and machine learning algorithms can be used by running screening of density functional theory calculations. We can accurately simulate the spatial arrangements, anchoring configurations, and energy level alignments of dye pairs before physical synthesis. Number two, to enable large-scale commercial market scaling, there is a need to transition away from irregular lab-scale dipping toward the standardized high-speed sequential dipping models. Then finally, to ensure long-term stability under real-world thermal stress, the industry must aggressively replace volatile liquid electrolytes with solid-state biopolymers and highly robust solid-state wall transport materials. In conclusion, this review establishes that molecular engineering via co-sensitization is an absolute requirement for the evolution of next-generation dye-sensitized solar cells. For high-efficiency synthetic dyes, combining organic structures with organometallic or porphyrin frameworks successively bridges the green gap in the solar absorption. This increases open circuit voltages to values around 0.9 or more, and also increases the power conversion efficiencies to commercially acceptable percentages such as 15.2. Concurrently, for sustainable natural dyes, despite their low absolute efficiencies, they have unique competitive advantages. They are completely eco-friendly. They have got exceptionally low cost fabrication, and they also display zero fabrication toxicity. Crucially, they also possess excellent low light stability, which positions them as a premier energy harvesting candidates for indoor Internet of Things and green wearable electronics. Ultimately, our final recommendation is a dual track approach. There is need to enhance the long-term operational stability of high-efficiency synthetic cells whilst expanding the underlying chemistry of natural extract systems for highly sustainable, decentralized power generation. Thank you very much for your time and attention. I am now open to any questions, critiques, or academic insights you may have.